Yeah, so hello everyone. Welcome to the Global Medical Physics Education Series. We are very fortunate today to have a very esteemed professor, Dr. Marty Pagel. So Dr. Pagel is a professor at University of Texas MD Anderson Cancer Center with his primary appointment in the Department of Cancer Systems Imaging. And today he's going to talk about some of the various ways one can generate contrast in MRI. And I can speak for myself. I'm very excited to hear this lecture. So I hope you all enjoy it as much as I'm anticipating to. So with that, Dr. Pagel.
For sure. I'll start sharing my slide here. Hopefully you can see this slide.
Yes, we
So
can.
does the first slide look okay? Great. Okay. Well, Dr. Wagon, I really do appreciate the chance to be here and to join the community here across the globe. It's a great time for medical imaging, and I particularly focus on molecular imaging, and I think that's also a great growth area. So I'd like to share how we generate contrast in MRI and to then give you the types of applications that can be used with this contrast. Let me change to another pointer here. So first, as you probably know, a lot of us are involved with MRI research or operations in the clinic. And clinical scanners on the order of $2 to $3 million US. A small animal scanner is $1.5 to $2 million US. Quite an investment. And so we do have to learn how to get good value from that strong investment. And I think of really three areas. Anatomical MRI is shown in this top row. You've seen many pictures like this, I'm sure, as well. This picture of the human brain happens to be a selfie. This is me. I'm always surprised at how large my tongue is inside my head. Of course, there is also vascular imaging. This is the human finger shown here, and you can see the joint within the human finger. Exquisite spatial resolution with MRI that sometimes is difficult to appreciate. And then here's a human brain image, and over time you can measure anatomy as well, right? To see changes in the human brain as our brains naturally shrink as we get older. So we have that to look forward to. There's also functional MRI. I'll just go through this quickly with the breathing in hyperpolarized xenon to look at lung function. Of course, vascular function all the way from the heart to the kidneys can be displayed. And then heart motion can also be studied with MRI. So great functional MRI. And I think of anything involving time as really being a functional imaging technique. And then finally, molecular MRI, as I mentioned, is starting to approach clinical translation now. And that could involve methods to look at protein content, enzyme activity, gene expression, to some extent, still challenging there. Metabolites with MR spectroscopy and other techniques, even oxygenation and pH and so on. And so to get at the molecular compositions of pathology will be the next revolution, in my opinion. And that can be seen with some colorful maps here that I won't have time to explain right now. And then how do we get these contrast mechanisms? And I'd like to pause and point out first that I'm going to start with the basic contrast mechanisms. Many of you are probably familiar with T1 and T2 MRI contrast, but we'll go through those. And then we'll get to the more involved mechanisms of arterial spin labeling and diffusion weighting and so on. And then finally to some mechanisms that are really not that common, but good to at least be aware of. And I'm really showing those to show the complexity of MRI. So there's a whole spectrum of contrast mechanisms. So if you're familiar with these at the beginning, well, you might be interested in those at the end. Or if you're not familiar with those at the beginning, well, this will be a good introduction for you. So as you may know, magnetization is excited into the transverse or XY plane relative to the magnetic field that we like to call along Z. And this magnetization then spins back to the Z-axis in this corkscrew motion. And while it's returning to the Z-axis, we can measure how quickly the rate of return to the Z-axis is, and that's called our T1 relaxation. And different tissues can relax at different rates, and we can time the experiment at a certain time of relaxation to maximize the difference in signal. The MZ represents how much signal we're going to get in the in a particular voxel, so we can tell different contrast. Or we can look at the disappearance of the magnetization in that XY plane, as shown here, sinusoidal signal oscillating along the y-axis or x-axis, and finally just disappearing altogether as the magnetization returns to Z. And again, we try to maximize the difference in signal strength in the image by choosing a time of evolution where the magnetization has evolved, maybe not very far for one tissue versus another tissue. And optimizing these TE and TR parameters is key. Also, I should point out real briefly that you would think that the T2 time, the rate of disappearing from that XY plane, is different than the rate of return, or the same as the rate of return to the Z axis. That's not the case because really we have many, many hydrogen atoms within any small piece of tissue. And therefore they might behave slightly differently and actually start to fan out or fray or become incoherent within this XY plane, while nothing has returned to the Z axis. And in that case, the T2 relaxation has to be faster. It has to disappear from the XY plane in a coherent net magnetization relative to Z. And so you might hear that T2 always has to be shorter, or the relaxation mechanism is faster than T1. And therefore they are different. And that leads to this chart right here, which I think really puts all of this together for you. That if you have a really long TR time, so you're very far out on this graph, and you have a very short TE time, so you're at the top of this graph, that's this proton density image shown in green in the lower left right here, where there is no real T1 or T2 weighted contrast. This is actually the total amount of hydrogen atoms or protons or spin density in all of those pixels within the image. But if I lower the TR time, to see a change in contrast between different tissues. Now you can see in this upper left, there is T1 weighting, a difference in contrast between different tissues, in cerebral spinal fluid regions and gray matter and white matter. Or if I change TE and make that longer and longer, well, I go down this curve until I find a difference in the two tissues. And here you can see you have some difference in brightness and darkness as well. And of course, optimizing both the T2 weighted and T1 weighted contrast gets you the image that you desire. And well, I really respect our clinical radiologists, but you know, a simple way of describing training in clinical radiology is that they spend years training their eyes to pick out small features based upon a specific TE and TR time to get that T2 and T1 weighted contrast. But if you do that, then you can see exquisite detail within the human brain, or here's a rat image in the axial plane, looking at a tumor within a kidney. In this particular case, I was able to then humanely euthanize the rat and check the tumor size. And the size that you get from gross pathology does match MRI, as we all know. But years ago, that had to be proven, right? So with good contrast, you can see features quite nicely. Well, we can use that to our advantage by making agents that we can inject into the body. And there are now 9 clinically approved contrast agents by the Food and Drug Administration here in the US. I believe there are slightly more, maybe 10 in Europe and so on, but not too many. And all of these agents do have a metal ion that can interact with water and make the water magnetization relax or return to the Z-axis faster than water that is not around these agents. And that can be seen here, where at no concentration of this agent, you get a very slow return to equilibrium. And as you add more and more agent, you get faster return. And because of the way we set up the experiment, faster return to equilibrium actually makes the image look brighter, which might seem counterintuitive at first because we're really detecting magnetization in that XY transverse plane. But the MR physics work out to be that way if you were to study a T1 experiment. And actually the 1 over T1 time, which is really R1 relaxation rate, a per second rate, that is linearly correlated with the concentration of the agent. So in theory, you could measure concentration using the brightness of the MRI image, a T1 weighted MRI image. But there are some complications along the way, so you have to be a little careful with that. But if you do that, you can then, and by the way, I should also mention you can measure the T2 relaxation time of these agents, which gets faster and faster, disappears from that XY plane faster and faster as the concentration goes up. And there you can also measure concentration using the 1/T2 relaxation rate as well. It's more common to use T1 than T2 in the clinic because these clinically approved agents are really set up to be T1 agents at 1.5 and 3 Tesla magnetic field strength in the clinic. Okay, so what is going on with these agents, right? And if you want to take a moment and write down these equations, that's okay. But I would not recommend it. That would be a lot of work, of course, right? So instead, what I would really like to highlight are the relevant terms in these equations for T1 and T2 relaxation. And really, it's the distance between the water molecule and that metal ion within the agent, R. So if you are able to get the water closer, you'll have more relaxation. And there are ways of hiding the metal from water and then having that hiding mechanism go away and have water get closer to the metal. And that can make a responsive agent and so on. Or correlation time, which is really the rate of tumbling of the molecule. And that rate of tumbling is based on viscosity and also the size of the agent as well. The reason that viscosity is important is that our different tissues do have different viscosities. Gray matter, white matter, tumor, muscle, spinal fluid is very non-viscous relative to other tissues that are viscous and so on. And really, if you think of it, this viscosity that it then relates to how fast a molecule can tumble is really dictating how bright these agents are. And therefore, something such as a tumor that can take up a lot of agent and has a very non-viscous environment has different brightness than a muscle tissue, and that adds to the contrast. So, and I'll skip this part. This just talks about the magnetic field strength and how correlation time plays into that. That's really an extra detail. Typically, we're working at 1.5 or 3 Tesla in the clinic, so not so relevant. But here's a case where this does come in handy, where tumors in particular have very chaotic blood vessels. They are very much like a mess of spaghetti noodles relative to normal blood vessels. And because of that, these tumors are leaky and allow agent to leak into the tumor area, while normal tissues such as muscle have some leakiness, but not as much. So here's a mouse with an axial image through the mouse. And if I inject this agent, you'll see that the agent starts to collect into the tumor up here on the upper right part of the mouse and gets brighter than most of the rest of the mouse. Now the bladder is also filling up as the agent filters through the kidney and into the bladder, which is a nice control organ, if you will. And you can see this is a nice a dangerous tumor. It's growing rapidly. It's got good vasculature. It's very leaky, so it can take up a lot of nutrients. And then after treatment, one day, you can see that this tumor doesn't have as much brightness, and there's even a black hole in the center, showing that, at least in this preclinical example, it's really nice to use MR contrast with the chemical agent to look at the difference in blood vessel architecture and leakiness. And there's a variety of studies done very commonly every day on all magnets to inject these agents, somewhere around a couple of maybe 2 million injections per year globally of these agents to just look at the brightness itself. But you could take that one step further and actually measure the brightness change over time. And these are pharmacokinetic and curves showing the rate or kinetics of the delivery or pharmaco properties of these agents into the tumor. So we can measure the rate of transport into the tumor and the rate of transport out of the tumor by doing quantitative analysis. Unfortunately, this is not done in the clinic very often because you need very good quality data. It's more for high-level research with mouse imaging, but can be done. And there's still research in the area to make this work better in the clinic. If you do this, you can see that combination drugs relative to just one drug and radiation can actually make tumors become more leaky or less leaky over time. And that can be related to whether the therapy is having an effect. So a good way of monitoring early response to drug effects by just seeing how the blood vessels are changing over time. All right, so there's an example of T1 weighted contrast getting bright over time using a chemical agent. combining molecular imaging and contrast together, which is our theme, right? Let's move on. Now let's talk about functional MRI, also known as fMRI. And could we use something native in the body as a contrast agent rather than having to inject a chemical agent? Well, yes, we can use hemoglobin. And hemoglobin that has oxygen bound to it is known as being diamagnetic down here on the bottom of the screen. So it doesn't have much magnetic property and therefore does not influence the magnetic field of the MRI system. So in the regular state, there's there's some oxyhemoglobin, right? But there's also a lot of deoxyhemoglobin, which I'm showing as HBr, which is paramagnetic. That iron in hemoglobin is not bound to anything else, so it acts like a little mini magnet in the blood vessel. And that will cause the magnetic field to change in this area where there's a lot of deoxy HBr hemoglobin. Well, you get a certain brightness of the image, that's fine. But then if you stimulate that area, you'll get more oxygenated hemoglobin to flow into that area. That will reduce the amount of deoxygenated hemoglobin. And you'll see that these lines on this basal state diagram are now gone after stimulating because we've reduced the amount of paramagnetic deoxyhemoglobin. There's more diamagnetic oxyhemoglobin that does not affect the magnetic field. And over here, you can see that there's variations of the T2 experiment that can be done that cause the image to look black when you have a lot of paramagnetic material, and less so if you have the diamagnetic material, right? You have more deoxyhemoglobin, you'll have a big black spot. If you have oxyhemoglobin, that black spot is much less in this particular case. So could we use this to our advantage over time? Again, functional MRI is based on time. Well, yes, we can have a control image first. Then we can stimulate a patient to think of something or tap their finger or have some other kind of response that will stimulate their brain. And you will see the signal in the image actually go up because the deoxyhemoglobin is being replaced by oxyhemoglobin that is rushing to that part of the brain. So there's more diamagnetic, less paramagnetic material, and the signal, the MRI signal is more pure, if you will, and therefore you can see it better. And then that effect wears off as the brain relaxes in that area. Is actually an undershoot. And then finally, the brain reaches homeostasis again. You can do this over time. Here is a case, I believe this was finger tapping, I don't recall, where the patient was asked to tap their finger, stop tapping, tap their finger, stop tapping. And you get a time series and you can take the average and get better quality data by averaging together. And you're able to see this brightness in the brain and the brain image that was actually consuming or was active and requiring more oxyhemoglobin to get to that area of the brain. So great contrast mechanism there of getting the diamagnetic agent to that part of the brain. So there's a whole field, now neuroscience departments buy MRI scanners and use them as a tool. It is no longer just for neuroradiologists. That's how common this technology is. It's just another machine in the neuroscience department. And there's just wonderful features that you can tell with MRI, looking at all of these different kinds of activities, motion perception, moving bodies, different scenes, memory, eye movements. When you move your eyes, this part of your brain is actually active right now in your head. I like this example on the side. Janet Husband, a colleague from many years ago, she's in the UK and she studied pain. And you can see that there are different parts of the brain that become active and have have oxyhemoglobin flow there as a patient's hand is placed in warmer and even very hot water. 61 degrees Celsius is actually quite painful. And you'll notice that the pain centers are actually more centered, not as diffuse, and really quite intense in these images, right? So here's the key. She was actually studying rugby players who have a different pain threshold than those of us who are normal humans. And she was able to show that rugby players do have their brains wired differently to accept pain relative to non-rugby players at the elite level. So I find that interesting. All right, so let's move on to another mechanism, arterial spin labeling. Before I mentioned that you excite magnetization and you watch it return to equilibrium at that same spot in the image. But what if we excited the magnetization down in the neck area of a human patient, but we actually detected the magnetization farther up in the skull, up in the brain area? Well, that would be labeling these the magnetization or spins of the arteries down in the neck area, arterial spin labeling, and then allowing that excited magnetization to then flow into the brain area where it is then detected. You don't have to detect at the same place where you excite the magnetization. So that's done here, labeling slab and imaging slices. You take a control image and a labeled image and subtract, and often there's a kind of noisy data, so you have to massage the data to really pull out the good contrast. But you can see there is some contrast here, some brightness and some less bright spots right here, right? Well, you could do this time and time again. That would be continuous arterial spin labeling by having a patient tap their finger or, again, repeated tasks. And you can see that the blood flow will of this excited magnetization will flow into a particular area of the brain and then stop and then flow again as that patient repeats the task. And that helps with the signal averaging. And again, you can map out brain function by looking at the flow of blood. The same idea of this exciting magnetization, T1 weighted or T2 weighted, and then detecting it elsewhere. You can even look at cerebral blood fluid areas during a cerebral ischemia, which areas of the brain are getting more or less blood than they should under normal cases, right? And here's a 24-hour follow-up after an ischemic event, and you can see there's been significant damage, right? Much lower blood flow to this part of the brain, unfortunately. You can even see areas of the blood vessels that have become attenuated over time with a very good resolution. So arterial spin labeling, very common in the clinic, now becoming more standardized in multi-center trials, thanks to a lot of collaborative work in the field. So it's moving along. So diffusion weighted, how does this work? Well, if I were to take a mouse or a patient and just look at the magnetization at 3 spots within the mouse, I have the magnetization in this transverse XY detection plane all ready to be detected from all 3 spots. And so let me then apply a gradient along the mouse. And so this magnetization spot in green will rotate by 180 degrees. Magnetization in yellow will only rotate by 90 degrees. And there's really no extra magnetic field applied at the nose here. So this magnetization spot in blue didn't move at all. And I'll go back and show that again. Here's ready for detection, but just before detection, I turn on this gradient and make the magnetization change in its direction. I can then apply the opposite field and have it go back. Now, if I do MRI, I'll get a standard MRI image, no change in contrast. Well, that's not very exciting. Let's do the experiment where we actually see diffusion weighted MRI happen, where with diffusion, I now apply that gradient, no change from what I discussed before, but now I wait. And that magnetization can now diffuse somewhere else within the mouse body. So when I apply the opposite gradient, things do not refocus back to where that original spot. You see that the spot in blue has actually now gone in the other direction. The spot in yellow has not quite returned to the y-axis as it did before. The spot in green also has not reached that. So you can watch how much magnetization dephases by doing this experiment with more and more delay between the 2 diffusion gradients, turning on and then turning in the opposite direction. And then you can watch how fast this magnetization becomes incoherent and loses its normalized MRI signal. You can fit this to a curve. You can get out a number called the apparent diffusion coefficient. Well, why is that important? Well, here are 2 examples where normal tissue has some cellularity, but not a whole lot of cellularity. There's some extracellular space. So the water molecules can diffuse between those cells pretty well. But if you have a tumor with a lot of cells that are growing very rapidly, often tumor cells are smaller on average and pack better than normal cells. Well, the cellularity actually goes up, and therefore the diffusion goes down. And that can be seen in this image here, where the contrast right here, shown by the black arrow, is actually quite low, because the diffusion is actually low in that area due to a lot of cell packing indicating a tumor. And then using a different imaging method, PET imaging, there was evidence that yes, that is the location of the tumor. Even these very small spots that you can see that are very low in brightness as well, and they matched the PET as well, relative to the bright spots elsewhere within this image, right? So you can detect tumors that have a lot of cells that form barriers to diffusion for the water molecules. Or you could treat the tumor, and by treating the tumor, the cells should loosen up and eventually disappear, become necrotic and apoptotic, and be taken out of that area of the body. And that causes more room for water to diffuse, and the diffusion rate will go up for the water. So you can watch the effect of therapy over time as the tumor cells are disappearing. So diffusion weighted MRI is really common within cancer imaging these days. There's a variety of different types of diffusion weighted MRI for brain imaging to study the directionality of diffusion and so on. And that's really a whole lecture in itself right there. But I hope you get the idea that the brightness or darkness within the image is controlled by how fast the waters can move in the body. Okay, a more intermediate or more advanced topic is this area where I work in called chemical exchange saturation transfer, or CEST. And it's part of a family of experiments that you may have heard of, and I'll show those experiments near the end. But just to begin with here, I have a molecule, could be a protein, could be a chemical agent that's injected in the body, and I have water molecules. And if I were to look at their signals of the NH and the H2Os, well, I would have lines like this that I could detect with MRI and turn into an image. And really that's showing that some of the magnetization, and by the way, I apologize for this green line. I'm not sure how we're showing that line here. But there's a net number of hydrogen atoms pointing with the magnetic field relative to against the magnetic field. And that's the whole reason we get MRI signal. But if I were to scramble the magnetization or saturate it with a radio frequency pulse, that would make this equilibrium diagram become equal. And therefore, half the magnetization is pointing with the field and half is pointing against. And that's the definition of saturation, this unusual term that's used in MRI for many experiments. We'll talk about magnetization transfer and some other experiments in a moment. Now, in this case, if there's physical transfer of two hydrogens between those two molecules, well, there's transfer of these arrows, and you can see that the water line now has started to go down as well, because some of the scrambling or saturation has now been transferred to the water. You know, another way of thinking of this, which is often not described, and therefore I want to take an extra moment to describe it, other water molecules can be affected. I'm often asked, okay, so, you know, how do you describe this? And I hear about a quantum mechanics description, which is confusing and not very fun with all the math. Is there an easy way to think of this scrambling or saturation when we turn on these pulses at for only a certain set of frequencies? And yes, and so here is the easy picture to keep in mind for the future. What if you excite magnetization from equilibrium down into this XY plane where we detect it? That's called a 90-degree pulse. Very easy. What if we then apply a pulse for 36,090 degrees? Well, the magnetization would go around 36,000 degrees plus another 90 degrees, and it would be no different if everything was okay in a perfect world. Unfortunately, there's always a little bit of error in the system, and you might have just a 0.5% plus or minus of the angle that you really want to tip the magnetization by. And if that's the case, then you'll 36,090 degree pulse plus 180 degrees in either direction really makes the magnetization fan out in all directions. So if you want to think of it as being a case where the magnetization pulse has inappropriately just fanned everything out in that ZY plane, there's no net magnetization. It's due to the imperfections in the magnetic field and pulsing. That's really saturation. So that's an easy way of thinking of it, right? All right, well, just to show one research example, have a chemical agent that we then scramble or saturate. It exchanges with water. And in this case, I've placed this molecule inside the inner tube here. There's no agent in the outer tube. And if I were to selectively scramble magnetization, finally I'll reach 5.6 ppm in this small experiment I'm going to run for you here. And you'll see truly that the contrast in the inner tube gets darker as I approach the frequency of this hydrogen atom with this scrambling pulse, because it's exchanging with water, right? And so again, contrast is really the key to all MRI. You got to see a difference in brightness. And we're now able to use the brightness to tell us about the chemical exchange rate. There's another hydrogen atom as well that shows this darkness feature on the agent. And then of course, if we scramble the magnetization of water directly, everything goes dark. You can't see any water in any of the tubes, and so on. So this is a highly detailed spectrum just for today. But we use this information of different peaks that have different chemical exchange rates, which can be used to get a ratio, which is related to pH, because the pH or acid content will change chemical exchange rate. So we're able to measure pH using MRI, and that's a molecular imaging method. And again, it's all based upon seeing this tube go dark or seeing the tumor go dark when we tickle it with the certain frequencies of radiation. All right, so this is not just CEST, it's really part of a whole family of techniques that you may have heard of. And so I just would like to briefly describe those. Again, if you have a protein, you can selectively scramble that magnetization so it no longer has coherent magnetization, it's saturated, and that exchanges with water. You can have the relayed nuclear Overhauser effect. Here we scramble magnetization of a hydrogen on a carbon. That then gets transferred through space to a hydrogen on nitrogen, and that physically transfers. So this first step is called the nuclear Overhauser effect, or through space transfer of energy, followed by a physical transfer. Or we could just do magnetization transfer, which is to highlight that proton again, scramble its magnetization, and then through space, like one radio tower talking to your standard radio, it sends radio frequency signals over to the water and makes the water behave differently as well. So these techniques are all related to each other. Oh, and of course, if you scramble the water magnetization itself, then water is suppressed, and you get to see other types of hydrogen atoms, such as fat or maybe even protein signals within tissues. So all these are little bumps within the spectra, and you can manipulate the contrast in different ways, from spin density to magnetization transfer. You can see the synovial fluid, very protein-rich fluid in the joint of the human finger. And here is water suppression, so you can even start to see the cartilage within the joint of the human finger at really beautiful detail here. So you can manipulate the contrast for what you want. So I'm going to go through this last part, or the second to last part, somewhat quickly, because it doesn't occur very often. But I want to include it to show that relaxation and contrast in MRI can occur from a very diverse range of activities. And sometimes it's difficult to understand why the contrast is the way it is. All right, just because you get some brightness and darkness doesn't mean it's because of the standard theory. There could be complications. So T1 agents, as I've mentioned before, are when water visits a molecule that has a metal ion in it and interacts with that metal ion. And that happens at a very fast relaxation rate. This whole chemical exchange phenomenon that I've been talking about happens at very slow exchange rates. But there's an intermediate range, and you can make agents, or there are endogenous proteins that do this effect, called T2 exchange. So what's happening here? Well, in a standard T2 experiment, you have magnetization at equilibrium. You apply that so-called 90-degree pulse, and you have magnetization in this XY plane. It starts to dephase, apply a 180-degree pulse, make it flip over to the other side of that 3D space, and then it will refocus. So really, this picture here on the very far right is no different than this picture over here on the left, except with different pointing in a different direction. But the size of that arrow has not changed. I'm showing that down below here for another hydrogen atom, but no different than up on top, right? So that's standard T2. What happens if we do that experiment again, but now we pause and we allow for chemical exchange? One of these hydrogen atoms can move over to the molecule on top, and one of the hydrogen atoms on the molecule on top can go down to the bottom. Well, you'll see that one of the blue arrows has now moved to the top diagram. Red arrow has moved to the bottom diagram, somewhat randomly, right? And it would be a random process. And now what happens? Well, if I apply that 180-degree pulse and have things flip around to the other side, that's shown here. And you can see that by then allowing for refocusing, not everything would refocus. There's some magnetization that's a little different than what it was previously up in this diagram. So these arrows as a sum become smaller. And so you appear to lose magnetization simply due to chemical exchange and not due to the natural dipolar T2 mechanisms. And this is actually a common mechanism that happens at very high magnetic field at clinical 7T, even a clinical 9.4 Tesla instrument that Siemens will sell to you for, if you have $8 million US, they'll sell it to you. So, and this mechanism becomes more and more prominent at very high field, showing again that contrast is complicated and there are a whole variety of mechanisms that change MRI. Okay, then finally, I have hyperpolarized MRI, which is also a research-oriented experiment now. There have been hundreds of patients scanned throughout the world, about 500 patients now at UC San Francisco, over 200 patients at UT Southwestern, for example. So we're in the hundreds of patients. They're certainly not ready for clinical yet. But yet it's worth discussing how this contrast occurs. Here you have that diagram showing that a lot of magnetization is pointing with the magnetic field. There's some against the magnetic field. Most of it cancels out. And so there's very little net polarization at room temperature for normal systems. But we can do a reaction that causes a lot of the magnetization to point with the magnetic field. The magnetization pointing against the magnetic field is flipped over. We do that by taking a C13 enriched metabolite, such as pyruvate, put that in a microwave, place the microwave in a freezer. It's actually at 4 kelvins, so near absolute zero in terms of a microwave. And you place the freezer in a magnetic field, so you have this pointing up and down of magnetization. Then you wait 2 hours, or maybe as long as 45 minutes with more modern equipment, to let that reaction cook and have everything point in the direction of the main magnetic field. Then here's the problem. You have to inject samples at 4 kelvins, heat it up very quickly, check the pH, rush over to your magnet and inject it into your patient or to your mouse model. And so there's a flurry of activity that happens after this 2 hours of waiting. And you only get 2 minutes to play with the signal before it all disappears. Well, you can do that with a clinical hyperpolarizer. It looks like a vending machine, or here's a preclinical hyperpolarizer for mouse imaging here at MD Anderson. Of course, you also need special C13 detecting coils, which are not always common in all clinics. And if you have money, well, if you have a lot of money, then you can buy all this equipment and get the experiment to work, and you will get a beautiful signal, very high contrast from molecules such as pyruvate relative to just standard pyruvate that hasn't been hyperpolarized, or other molecules as well. So what can you use with this? Well, this is really from Jim Bankson here at MD Anderson, where he injects pyruvate into patients as well as preclinical models, and he studies the rate of converting pyruvate into lactic acid. And you can see here on these curves that grow in and out, pyruvate is detected, and then immediately after that, the lactic acid MR signal is also detected within the image or in the spectrum. And you can see different effects of seeing this conversion of pyruvate into lactic acid, a metabolic step, and see how that's affected by certain drugs that would be anti-cancer drugs, or perhaps would enhance the effect, right? And so now we're able to study metabolism using MRI And again, to stay with the theme, this is molecular imaging, but really you're looking at a change in contrast within this image, a burst of this contrast over time caused by this hyperpolarization being injected and getting this beautiful signal. Finally, I'd just like to thank all the people who I work with here at the MD Anderson Cancer Center and at previous institutions. They've inspired me to do this work. And to be honest, they keep me young at heart, and I can't thank them enough. And so with that, I would like to turn it over to Dr. Weigand, and perhaps there would be some time for questions.
Yeah, thank you so much, Marty. That was an awesome talk. If there are any questions from the audience, you can either type it in or just shout it out. I guess in the meantime, I will ask you, so you spoke a lot about sort of the confounding effects of the inhomogeneities on the CES signal. What are some ways that can be used to counteract those I guess B1 inhomogeneities?
Yeah, great question. So for a variety of quantitative imaging techniques, measuring the true T1 time, T2, diffusion time, the CES effect as well, very quantitative to get a pH value. It is important to have very accurate pulses that shift the magnetization as you would expect, the B1 power. Also, the B0 magnetic field, you got to have everything at the same frequency, or that could also affect your quantitative numbers. And I think there are three ways of ensuring that you have good homogeneity, or you're accounting for that. One is the hardware. Just make sure you've got great hardware and you're shimming your magnet. That's a common thing, to have localized shimming to make things homogeneous. It only works to some extent. Second part then is to do other experiments that actually map out that effect to see how bad it is. And if it's within tolerance, you might get away with it and have some small error bars on your quantitative number, but that's okay. If it's out of tolerance, well, then you would not be able to measure accurately. So there are ways of measuring magnetic field power, pulse power and magnetic field. The third way is then to add that to your analysis. And I think that's perhaps the best way, because hardware will never be perfect. And our methods will never be perfect. And I would really like to emphasize that I very often have done this in my career, where I acquire data and only then I start to think of how to analyze it. And over time, I've learned that I have to make an experimental plan that includes the analysis along with the acquisition, so that I don't make a mistake while acquiring data, because going back and acquiring data again can be very costly and takes a lot of time. So you have to combine analysis and acquisition together to compensate for these inhomogeneities, and then you can build that into your plan.
Thank you.